So this is another one of those moments where we're kind of like making a transition from one topic to another. Because we did reactions, it had to balance reactions, and then stoichiometry, and that whole thing. And then we're like, pause that. We're going to do like a sidebar episode, and we're going to do some electrons. Why are they important? How they interact? How they do polarity? But we're like really just putting a pause on polarity, because in chapter 12, we're going to come right back to it. First, though, we're going to take this detour. We're going to talk about gases. The gas law stuff is pretty cool, though. There's some really interesting things you probably never thought about. Oh, okay. So like, how long could you make a straw before you can't suck up the soda out of the bottom of the cup? There's actually a limit, and it's like a hard limit. Yeah. This is why actually, too, if you know anything about wells, if you've ever lived out in the country, there's a maximum depth that you can drill a well before you actually have to drill a wider well to put a pump at the bottom. So the reason that sucking on a straw works, or the reason that a well pump works from the top, is because it's removing air molecules from above the soda or above the water in the well. And that creates a pressure difference between outside and inside. So then that pressure on the outside is actually what's pushing the water up the straw. But if you get to the limit where the pressure outside isn't enough, it won't go any higher. For a straw, roughly, that works out to 10.3 meters. I don't remember all the exact math to work out here, but essentially what happens is there's like 15 psi is like regular atmospheric pressure. So that's 15 pounds per square inch. So that means on every surface, for every inch of surface, there's 15 pounds of pressure. And essentially, if you take that and you translate it into a straw, the amount of pressure that you can lift for the cross-section of that straw, so let's say our straw is an inch square. So we've got this straw that has a really massive end, and then it goes up. The maximum amount of water you could lift with this straw is 15 pounds of water, because there's no more pressure after that to be able to push the water up the straw. And that depends on how big the straw is, right? So bigger straw, you're going to get to 15 pounds of water faster, so you can't pick it up as high. This actually is also why like the giant sequoias can only get to like a certain height. I don't remember what it is, because the capillary action that actually pulls the water up to the top of the tree is no longer strong enough to overcome gravity. So pressure is a force exerted per unit area. So like I mentioned, pounds per square inch, like 15 psi, is a force in pounds per unit area. So a square inch is an area. And this is another one that's really wild to wrap your mind around. That pressure is actually molecules of gas colliding with things. So that number of particles that collide with a surface determines the speed that they collide with it, determines that pressure. Oh yeah, 14.7 pounds per square inch. That's regular atmospheric pressure at sea level. So as you go up, that pressure goes down. If you can go below sea level, that pressure will be higher, because it's all of the gas between you and space pushing down on you. So when you're sucking on the straw to pull the gas, or to pull the soda up, the pressure on the outside will push down just until the pressure inside the straw is equal. So if you suck it up like halfway up the straw, the pressure inside the straw above the soda will be the same as the pressure outside the straw. So there's only a limited amount of gas you can remove, and there's a limited amount of pressure outside the straw. Yeah, so if you had in a perfect vacuum, with a perfect vacuum above it, and this is an example of that like well pump. So if you put the pump up on top, then the maximum that you can do is 10.3 meters. This is assuming some diameter of the straw. And so if you could get higher pressure outside the straw, you could lift it higher. But you can't just change atmospheric pressure. Actually, are there any questions about this? Because this is kind of a hard topic to wrap your head around. This one actually, oh, we don't have them here. Oh, like the iPad. Okay, let's talk about this first, and then we'll recap this next week. So kinetic molecular theory is a model for understanding the behavior of gases. The model predicts the correct behavior for most gases under many conditions, but if you get to some extremes, it falls apart. So really, we're just going to focus on where it does work. So this kind of first line is the important one. Oops. So these are the tenets, the principles of kinetic molecular theory, that we have a collection of particles in constant motion. So remember, air is made up of atoms, molecules, that are all flying around. So that's our collection of particles in constant motion. We also assume that there are no attractions or repulsions between particles, and that the collisions are perfectly elastic. So when one of those particles runs into something, it bounces off. When it runs into another particle, it bounces off without losing any energy. And we also assume that there's a lot of space between the particles compared to the size of the particles themselves. Which, if you remember when we talked about like solids, liquids, and gases, that's kind of like gases' whole thing, is that the particles are really spread apart, whereas in a solid or a liquid, they're like in direct contact with each other. This was one that was always interesting to me. The speed of the particles increases with increasing temperature. So when it's hot outside, like it was today, that means the air molecules around you are actually just moving faster. And as it cools off, they slow down. Because the temperature that you feel, the temperature that we measure, is the average kinetic energy of the particles. Roughly the average. So really, by using these four things, we can explain how gases behave in almost any situation. So kinetic molecular theory is consistent with properties of gas that we can observe. For example, gases being compressible. There's so much space in between all the gases that we can make that space a little bit smaller. If you make it small enough, they'll turn into a liquid. But liquids are not compressible. Gases are compressible, right, because of all that space. Gases also assume the shape of their container. So they're in constant motion, and they'll move in a straight line until they run into something else. That makes them not move in that straight line. They don't interact with each other. So this is why, too, like, smells in your house or whatever will travel throughout the entire house because those particles are moving in straight lines until they run into something. And odds are there's going to be enough of them, they'll bounce into things and go, through doors and anywhere inside the house. Also, gases have super low densities in comparison to solids and liquids. That's because there's so much space between between the particles themselves. So if you took 1 can of soda and boiled all of that soda into gas, and then captured the gas into cans, you would go from 1 can of soda to 1,700 cans of soda, full of just soda gas. I guess orange soda in this case. And that's because there's just so much space in between them. So pressure is a thing that's predicted by kinetic molecular theory. Again, we've got all these particles all moving in straight lines until they run into something. pressure is a result of those particles constantly colliding with a surface. So we've got constant collisions. So it's because of pressure that we can drink from straws, because when you're drinking out of a cup of soda, and you have a straw, there are particles that are constantly colliding with the surface of the soda that are wanting to push it. And when you don't have anything on the other end of the straw, there's also particles inside the straw pushing down on the surface of that soda with the same force. As soon as you remove some of those particles from inside the straw, they're no longer colliding with the surface of the soda on the inside, and they'll move up. And then variation in pressure causes weather, really in general. How far do I want to go here? Okay, man. We're going to get a lot into pressure. I think let's leave it there for now. I think that's a good place to stop and a good place to pick up. We talked about kinetic molecular theory, and that's kind of where we left off. Talked about pressure. Let's see. So like specifically with the straw, so if you're pushing down on, or not if you're pushing down, there's atmospheric pressure pushing down on the inside of the straw and on the outside of the straw. So when you suck on the end of the straw, you're removing some of that air pressure. Then the pressure outside the straw is greater than inside, and the liquid moves up the straw. And then we moved into kinetic molecular theory, which is these 4 principles. So I think I posted the link for this as well, but I found this cool sort of simulation of a box here. And so we'll keep coming back to this throughout the lecture today to kind of get a better, more interactive visual of what the different properties of gases or the constraints that we put on them, how those affect things. So here we've got, in regards to kinetic molecular theory, we have our collection of particles in constant motion. We can stop them if we want. There aren't any attractions or repulsions between these. So if you try to track just a single molecule or a single particle, it'll keep moving into a straight line until it runs into something or gets hit by something. And then the third part is a lot of space between the particles compared to the size of the particles themselves. Now this is where the simulation is maybe, we've got more particles in here, right? So that would be like, if we just had a few particles. There's a huge amount of space. But of course, if we wanted to simulate actually what particles would look like in a box, you could just look at a box full of air because they're so small and the space between them so large, you wouldn't see anything. And then we can even, we put just 10 particles in here. The last one is that the speed of the particles increases with increasing temperature. So we can actually take down here, and we can turn up the heat. As you watch those particles, they'll move faster and faster and faster as the temperature goes up. Or we can do the opposite and turn the temperature down. And I think one of the cool things that you can see with the simulation too is that not all of the particles are moving really fast. And not all of the particles, like there's that one right there in the middle, I just got hit. Some of them are moving slow. So it's the average speed. And of course, if we add more particles, we'll have a lot more speeds sort of throughout the container. But we'll come back to this. Let's see here. All right, so those are kinetic molecular theory. So keep these things in mind as they explain everything else. Dad's waving at the door. So kinetic molecular theory is consistent with the properties of gases. So actually, gases are compressible. I think we did do this slide last time, but with this demonstration, we can actually compress the size of this container. And if you note, so the pressure right now is 35 atmospheres. We can also make this larger, and that'll decrease the pressure. We'll see that later. We go back to here. So gases are compressible because we have all this space. Right, kinetic molecular theory, a lot of space between the particles compared to the particles of the size of the particles themselves. So we can take these particles in a gas and compress them, but in a liquid, they're already bumped up right next to each other, so we can't compress it at all. Gases assume the shape of their container. This is because they're moving in constant straight line motion. So it doesn't matter what the shape of the container is. Some of them will eventually find their way into every part of that container. And the gases have low densities in comparison with liquids, solids and liquids. Again, this is a fact that comes about because of the amount of space between the particles. If you have all those particles pushed up next to each other in, let's say, a can of soda, right? They're bumped up side to side. We put all that space in between them. Now, instead of one can of soda, liquid soda, we have 1,700 cans of soda gas, which might smell nice, I guess. Yeah, we definitely got here. So pressure is a prediction of kinetic molecular theory. Pressure is the result of constant collisions between the particles of the gas and the surfaces around them. And again, because of this, we can drink from straws or inflate basketballs or move air in and out of our lungs. And then variation in pressure causes wind, and changes in pressure can help predict weather. And I was trying to track the pressure going from last week into this week. I think it dropped because last week was really hot, and then suddenly today it rained, and now it's super cold. So pressure can help predict that kind of thing. Also wanted to, switch back to this for a second. So the pressure on the inside of this container, here measured in atmospheres, is from those particles inside the box colliding with the sides of the walls. So the pressure exerted by a gas sample is defined as the force per unit area. So the one I think we use most often here in North America is, or at least in the US, is PSI. So that's, let me just write it out, pounds per inch squared. So that's how many pounds of force are being put on the walls of the container per inch squared. So we can go back to this simulation. We've got our box, and actually we can switch this to, I can't do PSI here. Atmospheres is another unit of pressure though. So you can see our pressure right now is 16.3 atmospheres. What do you think is going to happen if I add more particles to the box? Will the pressure go up or will the pressure go down? So if I add more particles, we have more collisions. So if I add these particles, it's another 50. We go up to 23.8, add another 50, that's 31.2. So by adding more particles into the box, really by using this pump here, we increase the pressure inside the box because now there are more particles constantly colliding with the walls. So it's kind of the difference between being shot with one Nerf gun and being shot with 1,000 Nerf guns. It's a lot more force. And there are other factors that contribute to this. So if I change the temperature there, right? If we increase the speed of all the particles, now they're colliding faster, which means they have more energy, and will give us higher pressure also. Very tangible experience with regard to pressure is, if you drive up to Kings Canyon National Park, Sequoia National Park, the atmospheric pressure is lower, but the pressure inside of your ears stays where it was at equilibrium here in the valley. So as you drive up, the pressure decreases outside your ear, but you still have the same pressure inside your ear, and so that pushes your eardrum out. That's part of why, when you pop your ears, you can hear so much better because that tension's reduced. The same thing also happens if you go underwater, but even faster. So just diving 10 feet in a swimming pool will cause pain in your ear, where you have to go thousands of feet up to get that same sort of difference in pressure. So the units from the simulation and the ones that we use the most are atmospheres. So an atmosphere is the average pressure at sea level. So kind of normalize to that because it's basically the same all the way around the world. You can look into some stuff about how the moon actually pulls the oceans, and so sea level is different if you're closer to the moon. So the SI unit of pressure is the Pascal. So defined as 1 Newton per square meter. This is kind of getting into some physics stuff. So it's a Newton in a square meter. Now pascals, though, are a very tiny unit of force. So 1 atmosphere is 101,325 pascals. So atmospheres, if we're working at atmospheric pressures, are very, very convenient because they're whole numbers. More often than not, instead of the Pascal, we'll use the kilopascal. So 101.325 kPa. And you should also recognize that this is a conversion factor. So we can convert between atmospheres, pascals, kilopascals, and the other units of pressure that we'll talk about. We don't have these here, but actually at COS we have these mercury barometers. So essentially what you do is you take a tube of mercury and you fill it up completely. So you leave no air in the end. Then while you have the end covered, you dip that end into a bath of mercury. So this is all mercury down here as well. The height of the mercury in the tube to create this vacuum is the pressure, atmospheric pressure. So this was a very practical way to measure atmospheric pressure. So at sea level, that'll be on average 760 millimeters tall of mercury. So that's millimeters of mercury. You could do that in inches as well. Today's pressure was 750, I think it was 752 millimeters of mercury. So we're below that average, but we're also at about 300 feet of elevation above sea level. Last week was, actually I think last week on Tuesday it was 757 millimeters of mercury. You can also do this with water, but your column has to be like 10 meters tall, so not as practical as mercury. So this is a table from the textbook. This one's going to be very useful to memorize some of these units and these conversions, especially these ones here. So 1 atmosphere is 760 millimeters of mercury. 1 atmosphere is also, 760 millimeters of mercury is also equivalent to 760 torr. So aside from having to look up new conversion factors, these should be easy because we've done so much unit converting. If we have 1.25 atmospheres, we want to convert that into torr. What's our conversion factor going to be for 1 atmosphere, or for atmospheres to torr? Yeah, so 1 atmosphere is equal to 760 torr. So I'm going to have atmospheres in the denominator or the numerator? Yeah. So if we put atmospheres in the denominator, then our atmospheres cancel. I didn't get out a calculator. There it is. So 1.25 times 760 be 950 torr. And we should really place a decimal there because these would be, well, 760 torr to 1 atmosphere is exact, but. Okay, and then if we want to convert inches of mercury to millimeters of mercury, this one actually, there's a couple ways that you could do it actually. So we can use these numbers. What's our conversion factor between inches of mercury and millimeters of mercury? 29.92 inches of mercury, and then 760 millimeters of mercury. But remember that these are actually just the literal heights of the mercury in the tube over, well, it's actually just this distance measured. So it's millimeters to inches. So you could also do a millimeters to inches conversion. But we'll just use these for now. 30.15 inches of mercury times 760 millimeters of mercury over 29.92 inches of mercury. Because again, these units cancel. So we're left with units in millimeters of mercury. So this times 760 divided by 29.92. So it's going to be 765.8 millimeters of mercury. Okay, so we convert units of pressure just like we convert units of everything else. Right? We can just do unit analysis or dimensional analysis for that. Oh, one more example though. Okay, so if we want to go from inches of mercury to PSI, so remember pounds per square inch is PSI. We'll need our table over here again. So pounds per square inch is 14.7 PSI, is 1 atmosphere. And then 22.92 is our inches of mercury. So, sorry, did I say 22? I said 29.92. And 14.7. So 173 times 14.7 divided by 29.92. This is 84.99665,775. So because we only have 3 sig figs here though, we're going to be 85.0 PSI. Units to convert. Any questions about converting units? Don't try to convert this inches into square inches. You'll do weird stuff. Okay, so now onto these gas laws. So there's a relationship, measurable relationship between things like pressure, volume. We've got these different parameters that we're going to be playing with now. There's pressure, volume, temperature, and number of moles, or the amount of gas that we have. So if we keep all of these constant, or if we keep temperature and number of moles constant, how does changing pressure affect volume? So if we increase pressure, pressure goes up. Then the volume of that gas sample, volume will go down. And then the opposite is also true. So if the pressure goes down, the volume will increase. So we can go back over to the simulation. And you can see on the bottom here, if we switch from, this other one says intro, we go over to laws, and then we can hold some of these things constant. So if we hold a constant volume then, and we add in some particles here. Oh wait, let's hold a constant. Well, let's do this. Let's do this then. So if I take my volume and I decrease the volume so we have a smaller box, pressure goes up. If I take that volume and I increase the size of the box, pressure goes down. I don't have a way to directly control pressure because I have to add particles to increase pressure. Oh, there we go. So now it's adjusting the temperature to maintain. Yeah, okay. So this is the one that I wanted. Right, so decreasing volume increases pressure. Increasing volume decreases pressure. And you can think about this again in terms of kinetic molecular theory. If we have the same number of particles in this box, right, we still have 100 light particles. If we make this box bigger, there's more space for them to travel around in before they hit the sides, which means we have less pressure inside of that box. If we close this box down, now the distance they have to travel to hit one side of the box to the other is shorter, so they'll be hitting more frequently, so our pressure goes up. So in a bike pump, which is actually like the bike pump in the simulation there, when we pull up on the handle here, there's a one-way valve actually that opens up at the bottom that lets air into this chamber. Because by increasing that volume, it decreases the pressure, and pressure from outside draws air into the bike pump, kind of like sucking on a straw. Then on the downstroke, you're taking the volume inside of that pump and you're shrinking it, so the internal pressure increases, pushing the air into your bike tire. Or one time I had to pump up my car tire with a bike pump, and that took forever, just to get to 30 psi. So we can make this, or we can define this relationship mathematically. Now, this was actually Robert Boyle, so that's why this is called Boyle's law. So it's directly proportional, or sorry, inversely proportional. So if we increase our volume by double, so if we double the volume, our pressure will be cut in half. If we cut the volume in half, then our pressure will double. So this is called an inverse relationship. So this is our Boyle's law. It'll let you calculate for changes in pressure or volume what your new pressure or volume will be, assuming that temperature and constant number of moles. Sorry, constant temperature. Actually, I didn't try this before, but, because it doesn't say what the volume of this box is. So we're not really going to be able to calculate that. It's okay. We'll have an example. Oops. So you can do this experiment. oh man, I can't remember what these are called. So these are devices used for measuring pressure. And so why am I struggling with this? Oh. So you have some gas that's trapped in here. And as you increase the amount of mercury on the right side of this, so as we're pouring mercury into here, this height difference is now pushing on the small amount of air trapped in that space. So as we add more and more mercury, we decrease the volume here by, again, adding millimeters of mercury, right? So this is the same way that we measure atmospheric pressure, now applied to this small space. So plotting just pressure versus volume like this, you get a curve. And if you plot volume versus 1 over pressure, it's the inverse of pressure, you can see we get a perfectly straight line rather than this curve that's a little harder to understand. So again, like I was explaining with the demonstration here, the kinetic molecular theory explains why this makes sense, because if the volume decreases with the same number of gas particles, there are more collisions with the wall of the container. So if we give those same number of particles a larger space, there are fewer collisions. And actually here you can see the relationship here. Might be hard to see on the back, but I can't go down more than that. So if we have, on the left here, we have 1 liter, right at the top. So this is there's 1 liter inside of there, and we have a pressure of 1 atmosphere. We cut this space in half to 0.5 liters, and our pressure increases to 2 atmospheres. So here's a good example of the kind of question that I would ask for this on our exam next week. So if we have a cylinder equipped with a movable piston, again, this is a cylinder with a movable piston. So this is what I'm talking about. Has an applied pressure of 3 atmospheres and a volume of 5 liters. What is the volume of the cylinder if the pressure is decreased to 2 atmospheres? One of the key things for these questions is going to be correctly pulling the information out of the question. So in this question, we can see we have atmospheres and liters. So that's at least one hint that we're going to be working with Boyle's law. And Boyle's law, again, is P1 V1 equals P2 V2. So then we want to know what is the volume of the cylinder if the pressure is decreased to 2 atmospheres. So we're given another pressure. Again, this is why it's important to know what these units are, because they can give you a lot of information about the question. So if this is a Boyle's law question, then we're going to have P1, we're going to have V1, we're going to have P2, and we're going to have V2. So what is P1 and V1? 3.0, yep, atmospheres is our pressure 1, and then our volume 5.0 liters. And then again, atmospheres is a pressure, so our volume is decreased to 2.0 atmospheres, leaving V2 as the thing that we're looking for. So one of the ways you can figure out which one of these gas laws you're going to need is by writing down all these variables and figuring out which equation has only one variable unanswered. We're also told in the question, what is the volume of the cylinder? Okay, so if we got P1 V1 equals P2 V2, Then we plug in our 3.0 atmospheres times 5.0 liters equals 2.0 atmospheres times V2. Units, including your units in your equations for gas laws especially, is going to be really important. And if you're rough on your algebra, refresh that knowledge, because there's going to be a lot of algebra involved here in terms of rearranging equations. So for this one, we need to get V2 by itself on one side. So we're going to divide both sides by 2 atmospheres. Oops. 2.0. All right, so then when we get 2.0 on the right side here, 2.0 divided by 2.0 atmospheres will be 1. So those cancel out. And then on the left side of the equation, we'll get, just looking at our units here, atmospheres times liters divided by atmospheres. So the units of atmospheres, whoops, that was fun. Units of atmospheres will cancel out. And the only units we're left with are liters, which are units of volume, which is the answer that we're looking for. So 3 times 5 is 15. And then 15 divided by 2 give us 7.5 liters equals V2. So if the units don't work out, then you've done something wrong, or you should double check that you wrote in all the correct units for everything. But it's kind of a built-in check for, did I pick the right equation? Did I plug in the numbers correctly? It's one of the nice things about the gas laws. Okay, actually we're gonna take a quick break because Mrs. Cornell is here to do an evaluation. And so she'll give you guys a survey, and then I'll be back and we'll continue with Boyle's law. Pause. All right. So Boyle's law as it relates to scuba diving. Boyle's law explains why ascending too quickly is dangerous. So if you've been down at deep levels, scuba diving, that atmospheric pressure in your lungs, this is hard to see actually, is equaling the pressure outside. So if you go down to whatever, 20 meters, you have 3 atmospheres of pressure. The scuba diving regulator actually is changing that pressure as you're going down to make those the same. So if you try to come up too quickly, suddenly the air outside your lungs is now 1 atmosphere, and the pressure inside your lungs is 3 atmospheres. This actually applies to your blood as well. The amount of gas dissolved in your blood depends on the atmospheric pressure. So you can really, really hurt yourself by ascending too quickly and having that pressure change too quickly. All right, so let's say a snorkeler takes a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere to an unknown depth. The volume of air in the syringe at this depth is 7.5 milliliters. So what is the pressure? If the pressure increases by an additional 1 atmosphere for every 10 meters of depth, how deep is the snorkeler? So we've got a couple different steps here. The first one, I mean, it says it up here, Boyle's law. But again, we can look at the units that we're using and make sure that we're using the correct gas law. So we have 16 milliliters of air at the surface in our syringe and 1 atmosphere of pressure. So what is Boyle's law? P2, V2, yes, thank you. So we're looking for units of volume and units of pressure if we're going to be using Boyle's law. And then the volume of the air in the syringe at the depth, once the diver is stopped, is 7.5 milliliters. So we're going to have our P1, or V1, P2, V2. So pressure is 1 atmosphere at the surface. Volume is 16 milliliters. And then our pressure at the depth, we haven't been given, and its volume of the syringe is now 7.5 milliliters. So you can see we've got all but one variable in our P1, V1 equals P2, V2. And I'll just write this out again, P1, V1, P2, V2. So our P1 is 1.0 atmospheres. Our volume is 16 milliliters. Our new pressure, we don't know what that's going to be, that's what we're trying to find, times the volume of the syringe at that new depth, 7.5 milliliters. So right now we're actually solving for just this first question, right? What is the pressure at this depth? And here again, we'll be using some algebra. We'll do this for all of these, but for now, we could do 7.5 milliliters divide by 7.5 milliliters on each side. Because we want to get our unknown variable P2 by itself. So here we'll have, right, these will cancel completely. And then our units on our left side, we have atmospheres and milliliters on top. We're dividing by milliliters. So milliliters will cancel. And so we'll get 1 times 16 divided by 7.5. So 2.1 atmospheres is P2. Did I say 1.5? 2.1 atmospheres. So when you're using Boyle's law, or most of the other gas laws even, the only thing you need to make sure is that your units are the same on both sides of this equation. Because if we had milliliters here and liters on the right side, then liters will not directly cancel with milliliters when we divide. Or the same with atmospheres. So here our answer is in atmospheres, but this equation will apply if we had atmospheres in milliliters, or if we had millimeters of mercury and liters or kiloliters. But we can use atmospheres, millimeters of mercury, inches of mercury. The units on both sides just have to be the same. Okay, so if pressure increases by an additional 1 atmosphere for every 10 meters of depth, how deep is the snorkeler? So 1 atmosphere per 10 meters of depth is a conversion factor. So 1 atmosphere per, actually I should write it this way probably, 1 atmosphere per 10 meters. So if we have 2.1 atmospheres, then we can multiply by 10 meters, divide by 1 atmosphere. So our atmospheres cancels, and we'll have 21 meters deep. That's an example, probably a B level type question for the exam, right? Because you have to be able to synthesize your own, or I guess not really synthesize, but understand that this is a conversion factor. And then we could just use unit analysis to figure out how deep the diver was. Any questions? No? Crystal clear. All right, so that's what happens if we're just changing pressure and volume. If we change volume and temperature and now keep pressure constant, we have a different relationship. So why does hot air rise? And why can we use hot air balloons If you think about it, flying in a hot air balloon is a crazy thing to do because you have no control over where you're going. You go up, and then eventually you come down wherever the wind takes you. But why does this work? So if we heat a gas, it increases the volume of that gas at constant pressure. So at sea level, if you heat up gas, its volume is going to expand. The number of moles, though, is going to stay the same. So the mass doesn't change. We have the same number of moles, the mass doesn't change. So the density decreases. So as we heat this up, volume goes up. So that means we're dividing m by bigger and bigger numbers. And so density is smaller. So lower density gas floats, and higher density gas, just like wood, floats in water. This is a result of Charles' law. So you can actually, I guess, how would you do that? Actually, I don't know. I was going to say you can kind of do this experiment at home with a balloon. If you take a balloon, blow it up, and put it in your freezer, the temperature will decrease. So what will happen to the size of the balloon? If heating it up expands, it shrinks. Oh, I should have queued up that video. There's a video of a guy putting a balloon in liquid nitrogen, which is super, super cold, and it completely shrivels up. Okay, so this is essentially this experiment of increasing volume with temperature. So if you, again, let's say we're taking a balloon, we know what that volume is. We can cool it down and cool it down, and then it creates this straight line, and we can extrapolate that line out to absolute zero because we can't have a negative volume. So the coldest we can get, where all of the particles have completely stopped moving, is absolute zero. So where volume and pressure are inversely proportional, volume and temperature are directly proportional. And this relationship was discovered by J.A.C. Charles. It's a lot of names. A French mathematician and physicist who quantified this relationship. Charles' law assumes constant pressure and constant amount of gas. So we're not changing the amount of gas. And a direct proportion gives us this equation. So let's go over to the simulation. That didn't do it. This will do it. Okay, so if we weren't constant pressure. Can we do constant pressure? No, because this changes. Oh, yeah. Okay, so see, that's changing the number of moles. Let's reset this. All right, so let's add in some of these light particles again. So that's our constant number of moles. And you can see that we've got pressure here at 11.7. And if I change the size of this box, whoops, clicking on the wrong side. Change the size of this box. Oh, that's not constant pressure. Oh, because I completely reset it. Here we go. If we change the size of the box, our pressure stays at 9.5 atmospheres. But our temperature, let's do this in Celsius. Our temperature in Celsius will change. So if we decreased the volume here, this is the smallest volume, our temperature is negative 151 degrees Celsius. So what's going to happen if I make this box bigger? It's going to have more room, yes. Temperature will go up. Okay, now think about this in terms of kinetic molecular theory. If the pressure is the number of collisions in the box, why does temperature have to go up if I make the box bigger?
So why does it have to go up?
Yeah. So how do we maintain the same pressure? if pressure is the collisions on the sides of the box. Yeah, we have to speed up the particles. Because the particles have to be moving fast enough now to collide with the box at the same speed, at the same rate, right? But now they've got way more space to travel. So they have to be able to travel across that distance, but they've got more distance to travel. Okay. So Charles' law, we're directly proportional. So we take the temperature of a gas and double it, its volume doubles. One of the things here, though, that's key about this is that temperature has to be expressed in Kelvin because Celsius is relative. So for Boyle's law, pressure or volume could be whatever units we want to use. For Charles' law, our temperature has to be in Kelvin. And again, going back to the kinetic molecular theory, if the temperature of the gas sample is increased, the gas particles move faster. So for the pressure to remain constant, the volume must increase. So again, you could do this at home with just ice water, blow up a balloon, set it in boiling water, take it out, put it in ice water. The balloon will change dramatically in size. Okay, so a sample of gas. A sample of gas has a volume at 2.80 liters at an unknown temperature. When the sample is submerged in ice water at 0 degrees C, its volume decreases to 2.57 liters. What was its initial temperature in kelvins and in Celsius? So we've got V1, oops, actually let's do it this way. So if we've got P1, V1 equals P2, V2, that's Boyle's law. Charles' law is T1, V1 over T1 equals V2 over T2. So if we look at these again, we know for Boyle's law we're going to need pressure. If we look at all the units that we were given in this question, we don't have any pressure. So we know we're not going to use Boyle's law. So we're going to be using Charles' law. We're going to have V1, T1, V2, T2. So what is our V1? 2.80 liters. And then our T1 is our unknown temperature. V2 we have is 2.57 liters. And T2 is 0 degrees Celsius. So what's the first thing that we have to do? Have to convert it. To Kelvin. Do you remember how to convert temperature to Kelvin? Celsius to Kelvin? Yeah. Celsius plus 273.15 will give us Kelvin. So we're at 273.15 Kelvin at the end. So then we can just plug these in. V1 over T1 equals V2 over T2. 2.80 liters over T1 equals 2.57 liters over 273.15 Kelvin. So this algebra problem, for an algebra problem, is a little bit trickier. I'm actually going to move it up here. we got to get T1 by itself, but we also need T1 on top in the numerator. So we can multiply both sides by T1 first. So we'll get these cancel, and then that'll give us T1 in the numerator on the right side. So 2.80 liters equals 2.57 liters times T1 over 273.15. Now we can multiply both sides by 273.15 Kelvin, and then also, should maybe have done this in a different color. We'll also divide both sides by 2.57 liters. So 2.8 times 273.15 divided by 2.57 give us 297 point, we only have 3 sig figs. But we are not quite done. So 297.595 Kelvin equals T1. So for your answer in Kelvin, you'd have to round this to 3 sig figs. But then we can subtract 273.15, and this will be 24.4 degrees C. Are there any questions there? Yeah.
To go from Kelvin to Celsius, you just subtracted the 272.15.
Yes.
Okay.
Any other questions? Yeah.
So you went from can you please explain it one more time? I don't know, I got confused. So
Okay.
So you multiplied, right? Or yeah, multiplied the 273.15, right? The Kelvin to each side, and then you divided by 2.57 liters to get T1 right by itself.
Right.
All right. And then you went from Kelvin to Celsius by subtracting it, right? By subtracting 273.15?
Yep.
All right.
Yeah. So what would have happened if we had used a negative, if we hadn't switched to degrees C, or sorry, excuse me, if we hadn't switched from degrees C to Kelvin, we would end up with a real weird answer. Because we would get, I don't know how many spaces to do it here. I'll do it, if you want to see that example, I'll do that in lab. I can show you why we need to do this, because you get weird answers. Oh, no. The easy answer is that you would end up with 2.57 liters over 0 degrees C. And you can't divide by 0. And we can't multiply 0 by the other side to get an answer that makes any sense. So this is, sort of practically speaking, why we have to use Kelvin. Because you can end up with situations where you have 0 degrees C. Yeah, so don't do that. Oh, yeah.
I know the way you did it, but can we do cross multiply?
What do you mean by cross multiply?
Like, there's the equal sign, so you just do the x, where it's 2.57 liters to T1, and then 2.80 liters to 273.
Yeah. Yeah. So let me, I'll just add a page here. Okay. And then let me, whoa, where did it add that page? What just happened? All right, well, things got weird.
It's okay. I was just
Okay.
wondering if, like, if it's okay to use that route too, or would you
Yes.
prefer us to do it like that?
No. This is, I think one of the tricky things about algebra is that you can do things many different ways. And so you kind of have to figure out what works for you. Mathematically speaking, though, yeah, you could have done that. So if I took, this is what I wanted to add, just add a page. Okay, well, oh. I think this is, okay, that's better. So just looking at what you were talking about, So V1 over T1 equals, because the other thing you can do is also just rearrange this before you plug any numbers in. So in this case, we wanted to solve for T1. Wanted to put that on the in the numerator. So what is it, May? What Mai was talking about here was cross multiplying. So we take the T1 and we'll multiply, essentially we're multiplying both sides by it, and it'll put it up on the top right, and the T2 will go on the other side. So this is now, I keep doing that, V1 times T2 equals V2 times T1. And then you divide both sides by V2. So those will cancel. But yeah, it's algebra. Okay, let's move on then. If we have a gas in a cylinder with a movable piston, again, that's that picture from before. Cylinder, sort of like our piston. This can go down or it can go up. Has an initial volume of 88.2 milliliters and is heated from 36 degrees C to 155 degrees C. What is the final volume of the gas in milliliters? So again, we can do a comparison between Boyle's law and Charles' law. And so this would be, every time I write the temperature first, V1 over T1, V2 over T2. And we can look at the units in our question and say, okay, we have initial volume. All right, so volume, both of these do have volumes of 88.2 milliliters. But we're heated from 36 degrees C to 155 degrees C, both temperatures. What is the final volume of the gas in milliliters? Again, milliliters. So again, we don't have any pressures, so volume, temperature. Yeah, we want to use Charles' law, not Boyle's law. So V1, T1, V2, T2. So we're even told initial volume, 88.2 milliliters. What's our initial temperature? 36 degrees C. Mm-hmm. And then our final temperature, 155 degrees C. And so milliliters is the thing we don't know. Okay. So let's try this other strategy of rearranging this before we even get started. So V1 over T1 equals V2 over T2. What we want to find is V2. So let me actually just, right, with a highlighter there. So here we don't need to cross multiply because we already have V2 in the numerator. It's already on top. So we can just multiply both sides by T2. So we'll get T2 times V1 divided by T1 equals V2. Yeah.
Because the T2s cancel out, right?
Yes, on the right side.
Because you're trying to get V2 by itself.
Yes. Right, yeah. So this is kind of the whole thing with algebra is that you're trying to cancel things out on one side to make them disappear. Because when we divide T2 by T2, we get 1. Multiplying or dividing by 1 is just itself, so we leave it off. We still need to convert our temperatures here. So we're going to add 273.15, 273.15. Move those over. So this is going to be 273.15 plus 36. This is 309.15 Kelvin. 155 plus 273.15 is 428.15 Kelvin. So we can just plug these numbers in. 428, whoops, 0.15 times 88.2 milliliters, sorry. Kelvin. And then we'll divide by 309.15 Kelvin. And that'll give us V2. And again, look at our units. So Kelvin will cancel out Kelvin, leaving us with units of milliliters. Yeah.
So are milliliters and liters, those are like the two units that are for volume?
Yep. It could be possible, excuse me, because the only other units, SI units of volume that we've talked about, and these will all be with the SI units, are like centimeters cubed. You could use centimeters cubed here. You could use meters cubed. They will still work correctly in this equation. So ultimately, it depends on what is the question asking for. So if you don't have to convert anything, don't. 428.15 times 88.2 divided by 309.15. Oops. So V2 equals 122 milliliters. Yeah.
So for the sig figs, are we looking at the 88.2 and then like the lowest number sig figs, right? Or was that for like a
Right.
you mean 36? So it's 122 because of the
Oh. It would be 3. Okay, so yeah. Because here I didn't. If we're adding or subtracting, it's the smallest number of decimal places.
Yeah.
So this would still be 3 sig figs. Because it's 0, no decimal places is the smallest. Yeah. $122 there. Any other questions? I'll say one of the other things that I think is nice about the gas law problems is you can kind of check to make sure that your math turns out right. And that did things move in the right direction, right? So we just talked about how Charles' law, as you go from a cold temperature to a hot temperature, volume increases. So for this question, we're going from 36 degrees C to 155 degrees C. So our final volume, or V2, should be larger than our initial volume. And this won't always catch mistakes, but it can sometimes. So here, 88.2, we went up to 122. So volume increased with temperature increasing, we're good. All right, so let's, how much is there here? Yeah, let's finish out with the combined gas law here. We'll just do a couple more examples. So we can use Boyle's law and Charles' law together in the combined gas law. So now the only thing that we're keeping constant is the number of moles. So now we can change two variables and solve for the third variable. And then if you think about it like this, if we've got our equation here, P1 V1 equals T1, or over T1 is P2 V2 equals T2. If V1, let's say we keep volume, wait, that's one of the ones that we haven't done. If we do constant pressure, so if pressure P1 is the same as P2, and let's just give them some numbers here. Let's say that these are both 10 atmospheres. Then any change in volume or temperature will give us V1 T1 equals V2 over T2. Because when we rearrange anything to solve for one side, 10 atmospheres, so if we move P1 over here, 10 atmospheres divided by 10 atmospheres will cancel out. If we make temperature constant, say it stays 0 degrees C, 273 Kelvin, if we wanted to solve for a change in volume, and we move temperature over to the other side, then if this temperature and this temperature are the same, 1 divided by the other will be 1, and they cancel out. So from the combined gas law, you can get Boyle's law and Charles' law. They're just kind of mushed together into one. So the key for figuring out if a word problem needs the combined gas law, again, comes down to remembering what these are. P1 V1 equals P2 V2. So Boyle's law. And then V1 over T1 equals V2 over T2 is Charles. And the combined gas law is P1 V1 over T1 equals P2 V2 over T2. So you can see how this part is the thing on top, right? P1, V1, P1, V1. And then if we leave off the pressure on these, then V1 over T1 equals V2 over T2 is Charles' law. So when we look at this question, we have a gas sample with an initial volume, 158, and a pressure of 753 millimeters of mercury, and a temperature of 34 degrees C. So that right there, just having three of those variables, should be a hint that you should be thinking about the combined gas law. And then if we take that gas and we compress it to a, again, volume of 108 milliliters and heat it to a temperature of 85 degrees C, what is the final pressure in millimeters of mercury? So because we have an initial volume, pressure, and temperature, as well as a final temperature, volume, and asking for a final pressure, we need the combined gas law to solve this problem. So we'll have P1, V1, and T1, P2, V2, and T2. So what's our initial pressure?
735.
Yeah, 735 millimeters of mercury. And then our volume was 158 milliliters. And our temperature is 34 degrees C. Our P2 is what we're looking for, right? What is the final pressure? So we don't know that one. Our V2 is 108 milliliters. And our final temperature, our T2, is 85 degrees C. So the combined gas law has the same restrictions as Charles' law in that we need to be using Kelvin and not Celsius. So we need to add 273.15 to each of these. So 34 plus 273.15. $307.15. Then 85 plus 273.15 give us 358.15. And then we'll write out our equation, P1, V1, T1, P2, V2, T2. So we're solving for P2. We just need to get the rest of these variables, V2 and T2, away from it. So we can multiply both sides by we're going to multiply both sides by T2, and we're also going to divide by V2. So when you're trying to cancel things out on one side, because we have V2 in the numerator, we put V2 in the denominator of what we're trying to cancel out, and same T2, T2. So they flip places. And so this will be, you have to multiply in the same thing on the other side, T2 over V2. So we'll get T2 times P1 times V1 over V2 times T1 equals P2. And if you can get that far, all you have to do is plug in your numbers and make sure you plug them into the right spots. So on top, we need our T2, so it's 358.15 Kelvin times P1, which is 735 millimeters of mercury, times V1, which is 158 milliliters. And then we divide by 108 milliliters, which is our V2, multiply by V1, 358.15 Kelvin. It's bigger. So, switch colors. If we look at this, again, we want to get the pressure. So we should have, and we do, we have Kelvin divided by Kelvin, and we have milliliters, well, milliliters here divided by milliliters here. So the only unit that we're not canceling out is going to be our millimeters of mercury, which are the units that we're looking for. But we do have to multiply all these things, so 358.15 times 735 times 158, and then divide by 108, divide by 358.15. So then our pressure is, if I did my math correctly, 1,075.28 millimeters of mercury. Whoops. Gosh darn it. So to use the correct sig figs here, we want 3 sig figs as our smallest. So this is 1.08 times 10 to the 3. Wait, let me try this again then. 350. Oh no. I used the wrong T1. That should be 307. What was the answer that you got?
1253.82.
Okay, cool. Verification. So 1.25 times 10 to the 3 should be the answer. All right, we'll kick things off with another example next week. I think that'll be good. Oh, and also next week, I'm going to show up an hour early. Well, I'm going to start showing up an hour early before lecture as like an office hour. So I'll just be here hanging out. If you want to come in and ask questions, you can do that.